بسم الله الرحمن الرحيم.
Hello everyone. Today we are doing a strengths of materials problem which is applied to a bracket. This is a very good problem to solve because it's going to give you a very good understanding of strengths of materials or mechanics of materials if you have a different name for that class. This is the same class, is the same topic. And this problem could really help you boost your first foundation in machine design if you're taking that class. So, you're given a bracket. We have a section C, which is the beginning of our bracket, go all the way to B, which is 3.5 inches long. And we are given a BA section, which at this point the bracket bends and give us a 2.5 inches from the B to A. Now that we have our dimensions, we are given that the vertical coordinate system is Y, so up and down is going to be our Y. Right to left is going to be our x-axis, and our third dimension, which is in and out of the page, is going to be our z-axis. Now we are given that there is a force 1 at 600 pounds applied at cross-section A downward in a negative y-axis. Now in our cross-section B, in the middle of a bracket, assumedly, there's a force 2 of 2,500 pounds applied. Given all these circumstances, they want us in 5 parts to find out the force, the moments, to find the principal and shear stress values that we need using Mohr circle all the way towards the end. So for part A, they want us to find the free body diagram and the coordinate system that we're going to use. We also want to find the forces, moment, and torques at cross-section C. This is our coordinate system, same as they give us. Y-axis is the vertical, x-axis is our horizontal, and our z-axis is going to be in and out of the page. It's going to be our third dimension. Horizontal is right to left, and vertical is up and down. For the free body diagram, we have to draw the bracket. There is many ways to do this free body diagram. This is not the only correct answer to the free body diagram, but in my opinion, is the easiest. We're going to treat this whole bracket as one system. We're going to go at part A and draw the force down and say that was our 600 pounds force. We're going to go to cross-section B and apply our 2,500 pounds in Z direction and write that in our free body diagram. What is going to be changed? Now point C is right now took off from this bracket, and we have to find out what is that thing is. That is a fixed support. So you're going to have 3 forces and 3 moments. However, we are not going to have a moment at Z because this bracket, I believe, has a torque of 0 because we're only given a Z force and a Y force. Because of these two, we're not going to have a Z moment or Z torque. We are treated with 5 unknowns at our point C. We have a moment around the Y, we have the moment around the X, and we have 3 forces on our point C, the CY, the CZ, and the CX. Now that we obtained our free body diagram and find what forces and moments that we have, now we can do our sum of the forces to find all the forces that are going to be acted on this bracket. Now, for the X direction, we know is going to be 0 because there's no forces in the X direction. This is the same similar reason as because we have a force in the Y and a force in the Z, we are not going to have a moment, torque, or torsion in the Z direction. Now, for the forces in the Y, we do know that we had a 600 pounds force applying on cross-section A downward. And because upward is our positive Y direction, we are going to say that CY is positive. and negative 600 because that 600 pounds force is acting downward, equal to 0. Solving for our Cy will give us a 600 pound force for our Cy positive. Which means our Cy is acting, as we were assuming it, is acting upward. Now for our Cz, we have told that going out of the page is going to be positive. We do have a Cz, and we do also have a 2,500 pounds force acting at cross-section B. Because that 2,500 pounds is going into the page, it's going to be negative because we just said out of the page is positive. Cz therefore is going to be positive because we have assumed the Cz is going to be into the page. Now we did that, we're just going to find Cz doing this, and we find that our Cz is 2,500 pounds. Now that we find our forces, we have to find the moments and torques that we have. As I told you before, we only have a moment around y and a moment around x. But I have lied to you about one thing. The 2,500 pounds that we have is not going to really do anything regarding this problem that we have. Both moments are going to be 600 times 2.5 inches that we have, and the both moment that we have are going to only be applied by the forces at the cross-section A, the 600 pounds. That is also because that 600 pounds is applied towards the end of the bracket. I'm thinking the 2,500 pounds is not going to do anything because it is applied into the middle of this bracket. Now, if I'm wrong, definitely let me know in the comments. We're also going to have a torque at the x direction, which is positive. But this torque is a twist that happens in this bracket. This twist is also the same thing as the x moment that we have, because it's again the 600 pounds that we have times the 2.5 inches that this is away from our cross-section C. So the torque, the moment at the y, the moment at the x are all same 1,500 pounds times inch. Again, this is just because the 600 pounds force that we have across section A is applied towards the end of the bracket. The 2,500 pounds force, even though could have caused any moment, because it's applied into the middle of this bracket, it really doesn't have any effect on the moment and the twist that we have. Before I go ahead and find the torque and the stresses that we have in this bracket, we are going to find out the distributions of the force and the moment in this bracket. For doing so, we have to cut through this bracket, the entire length. So it's going to be 2.5 plus 3.5, which is equal to 6 inches. That's the entire length of this bracket if it's not bended. We're also going to assume that we have bend this bend part of this bracket into a straight position. We're going to straight this bracket out, and we know the full length is going to be 6 inches. Now, doing so, you're going to put the 2,500 force that we had at point B, the 600 pound force that we had at point A, and then at point C, as we cut down, you're going to have the positive directions of our forces. If you cut this from the right hand side is cut, and the left hand side is what we're looking at, the normal force is going to be away from the bracket that we have. The internal shear is going to be acting downward, and our moment is going to be from the bottom all the way to the top. Always, always, and always. When you're cutting through this material, the moment that you have is from the bottom all the way to the top. And it's going to go away from the bottom and goes towards the top. So here, this is why our moment is counterclockwise. If I have cut this from the left and I had the right side to be my object, then our moment would be clockwise. Now, doing so, we know that normal force is going towards the right. Doing this summation of forces in the z direction, we find that we have the normal force plus the 2,500 pounds force equals to 0. So our normal force is negative 2,500 pounds. even though we are not going to even analyze this normal force in our distributions, it's just there that we calculate that. The summation of forces in the y upward is positive, and I forgot to mention to you guys that in the normal force we are saying that going towards the right is positive. So that's why the normal force and the 2,500 pounds are going to be positive, and then you get the negative normal force value. Which basically that means the normal force is supposed to be acting towards the left instead of right. It's just the direction. The y direction, we're going to say the upward is positive, and we're going to have both forces acting downwards again. Both forces acting downwards. And again, in the scenario that we have negative 600 and negative v. So our internal shear force is going to be negative 600 pounds, which is basically saying that an internal shear is not supposed to act downward, it's supposed to act upward, equal to 0. Now we're going to also find our internal shear force. For an internal shear force, we are doing it upon this point C. What do we have? The internal shear force goes away, because it is at point C. The internal normal force goes away, because it's acting at point C. The 2,500 pounds force is also going to go away, because even though it's acting at point B, it's going right straight to the C. We know if you want to have a moment, the force has to be perpendicular to the section that we have. This is why we are only going to remain with the 600. So the 600 times x, and is negative because the 600 is acting downward, or is actually positive, but we're going to have 600 times x, which is the distance that we have. And in this positive moment, why? Because it's acting counterclockwise. Using the right hand rule, acting counterclockwise, which is our positive direction. So, once we find our internal shear force and internal bending moment, we can find the distribution through this bracket. We know that our internal shear force is negative 600 throughout this whole bracket. So for the whole 6 inches, that is negative 600. And we're going to do that by doing the shear force diagram and show that it goes constantly all at negative 600. This is what is with the shear force. We know if there's a force happening, there's always constant at that value. If we have a distributed load, this shear force is going to be linear. That is what is going to happen to our shear force. Now, here comes the moment. The moment is the derivative, another derivative, my bad, is the integral of our shear force. So the relation between them is m equals to integral of our shear force dx. We have a constant. What is the integral of a constant? It's just x. So we have a negative 600x as we saw in our equation. That kind of proves it to what it is. And also that is why the force times a distance is our moment. This is why we had an x there. Therefore, our moment in this distribution is a linear path. You're going to start from 0, and you're going to go down all the way times the 6 inches to get 3,600, negative 3,600, which is where we're going to stop with our moment. And obviously this moment is going to come back all the way in. That is how our moment diagram is going to look like, moment bearing diagram. And we just proved how our relation between the shear force and the moment diagram works. Now, in order to move on for the torque, we have to realize we have a cross-section H. When we had a cross-section C, we see that, as we told you guys when we cut it, the bottom part is going to be in tension. The top part is going to be in compression. Now that we know that, we know there's a neutral axis that divides these two parts together in half. Based on that, we have to look at what area are we looking for. We had an H and a K area, but the question that you're doing only wants to ask about H. So if you look at the H is at the top part of this section that we have. What does that mean to us? Because we are doing the H section, we are not at the middle. And at the top, the bending diagram, the bending stress is the maximum value that it can have. So our sigma bending is going to be our sigma max. However, for our transverse shear, we're not going to have any value because we are not at the neutral axis. That's why our transverse shear stress is 0. If you are at part K, the situation will be different. Our stress of the bending will be 0, and our transverse shear will be the maximum. But we are only working on H, so our transverse is 0, our bending stress is the maximum value. So we have normal, we have transverse. We all know that when we had our moments, they were both 1500. In order to calculate our stress, our normal stress, we need to find the total moment of the system. The way we can find that is to use the Pythagorean theorem, and we have to square our mx and my and then take a square root. If you do that, we're going to get 2121.32 pounds times inch. That's going to be our m total. You already have proof that our transverse stress is 0, so we don't have to worry about it. 4 times the internal shear over 3 times the area is going to be 0 just because, as I told you, you're finding all of the forces and stuff for the H part. We don't have to worry about the transverse. Now we're going to do the bending. For the bending, we find our m total, but we don't know our centroid that we needed, and we do not know our moment of inertia. How can we find it? For the inertia, we know is the centroid squared times the area squared. We know for the centroid squared, if you want to find it, because you're looking at a circular cross section, it's going to be diameter over 2. So it's 0.8 inches, 0.8 inches divided by 0.4. So you'll divide it by 2, we get 0.4 inches. That's our centroid. We're going to square that and multiply that by area, which the area is pi over 4 times d to the d squared, which is d is 0.8. So we're going to calculate our area as well. And once we have our area and the centroid, we're going to get 0.0804 inches to the 4. Now we know our centroid, now we know our moment, now we know our moment of inertia. If we calculate all these together, the 2021 times the 0.4, and then divide that by 0.0804 that we just calculated, what we are going to get is our sigma bending, or the stress bending, is going to be something in 29,000, but that just going to tell you that this unit is in PSI. If you want to find that in KSI, kilo PSI, you just divide that by 10 to the 3 and get 29.84 KSI. So as we told you, we're going to have a torsional shear stress. How do we find that? It's going to be the torque times the radius, or the polar moment of inertia, if I'm not mistaken, because this is to the 4 just like the other one. This is a bit different because, as I told you, the other inertia that we find out was centroid squared times the area. Not really on this one. On this one, we also have to realize that we are in a round section. This bracket is not having an empty section or hollow section. There's not a hole inside this bracket. If you had a hole, the situation for our polar moment of inertia would be different. We have to subtract the diameters that we had, the inner and the outer diameter, the diameter of the hollow section, the diameter of the part itself, or the solid section. Once we did that, then we could have multiplied that by pi over 32. But here we can just assume that we have a solid round section, which we do, is kind of given to us by the drawing. So we're going to do that, the pi times d to the 4 over 32. We know d is 0.8. So 0.8 to the 4 times pi divided by 32 will give you 0.04021 inches to the 4. Now we know that one. And we know for radius, from the centroid that we had, 0.8 divided by 2, the diameter divided by 2, gives us 0.4 inches. Now that we did that, we're gonna all apply the stuff that we have. We know our torque is 1500 based on the earlier calculation. We're gonna plug those all in and we get a torque of 14.92 ksi. Again, when you put all these numbers in, you're gonna get something about 14,000. But divide that by 10 to the 3 to get ksi, you'll get 14.92 ksi. So, we're gonna find our stress of axial because we're gonna also have a stress axial into this part. Once we do that, we're gonna have force over area. In this case, force is P. Now remember how we didn't use the 2500 somehow all the way through n? We're gonna use it for axial because we haven't used it for anything else. This is gonna get applied on axial. On axial, our force is gonna be 2500 and it's gonna be divided by area. We know the area of a circle is pi over 4 times d squared. That's what we're gonna use. We're gonna apply the 0.8, solve our area, and get 0.5027. You're gonna get 26 and some numbers, or just round it here for you. 2500 divided by that area is gonna give you a sigma axial of 4.97 ksi. We will need all these values that we have in order to do our state stress elements. There's going to be the stresses that we want and the shear stress that we just got from this bracket in order to do the Mohr circle. And that's going to be our last step. The Mohr circle will be our last step for the day. So how are we going to do that? We know that TXZ for that stress element is only one thing because we didn't have transfers. If we had transfers, that transfers would be added or subtracted from this torque. We don't have it, so our shear stress for the state element is going to be equal to our shear stress of a torque, or torsional shear stress that we had. So it's 14.92 ksi. But for our sigma z, our stress in the z direction, or stress in the x direction, actually in the z direction, my bad, because we were looking at h. So stress in the z direction, as it goes towards the sides of this area of h, is going to be our total normal stress minus our normal axial stress. We're going to subtract these two together. Remember we had a 29 something for our stress of the total. And now we have 4.97. 29 minus 4.97 will give you somewhere around 24.87 ksi. As proven based on the last steps that we did, we're not going to have a stress in the x and we're not going to have a stress in the y. All going to be 0 because we didn't have anything for them. This is also because these stresses that we have, we are looking at h. H was on the top of this bracket. There is nothing really be added on the x. Remember that we did in the beginning, we didn't have a cx. We didn't have any force on the x direction. So this part is actually our sigma x. We don't have anything added vertically for us, so we don't have sigma y also. All we have is sigma x, which is our shear stress in the z direction, 24.87. For our shear stress, we already find it. It was our torque, so it's 40.92, and it's positive. Now that we did that, we have to find our radius and the center for our Mohr circle. For the radius, as you can look, I have actually sigma x minus sigma y. Now you may have a question, weren't those 0 over there? It depends on what stresses that you have here. In this case, you only have shear stress z, so you only about z. And this question is basically our stress in the z direction minus our stress in the x direction. We don't have any stress on x because our stress in x is right now our stress in y in the equation, and the stress in z right now is our stress in the x by the equation. So if I want to actually do that correctly, our sigma x is sigma z, and our sigma y is sigma x. We know sigma x is 0, no stress there. So stress as z divided by 2, which gave us 12.435, plus, and you're gonna also square that, I forgot about the square here, and then plus the shear stress squared, which was our 14.92. We're gonna square that we're going to add these two numbers together and then take a square root. So our radius is going to be 19.43 ksi, doing all those calculations. For the center, again, we have sigma x plus sigma y over 2. And this center is sigma x is sigma z, because in our horizontal, and sigma y is sigma x, which is in our vertical, based on looking at area of h on the bracket. Doing so, we only have sigma z over 2. So it's just 24.87 divided by 2, which should give you 12.435, as we actually found it in this first part of the radius. So our center is 12.435. For the last part of this question that we have to find our principal stresses and the maximum shear stress based on Mohr circle. In Mohr circle, we find the center and the radius. That's the whole point. We find the center of our circle and the radius of our circle based on the state element stresses that we have, either normal, transverse, or torque. Using those, we can find our principal stresses. You have to know that sigma 1 has to be the largest, sigma 2 has to be in the middle, and sigma 3 has to be the lowest stress that we can get on the circle. If we get our center, which was 12.435, and add that to our radius, or add the radius to our center, basically, 19.43 plus this 12.435, we will get 31.87. That is going to be the largest stress that we can have in a Mohr circle. So that's going to be our sigma 1. Usually when we get our center and subtract that by our radius, usually that's going to be our sigma 2. But that is in the case if our sigma 2 is positive, is not negative. In this case, you have 12.435 minus 19.43 is going to give us a stress value of negative 6.985 ksi. Because this is negative, we have to think about something. When you're doing this state element stresses, you're thinking 2D. We are not taking 3D. Since we're doing this in 2 dimensions, you have to realize we're getting rid of a dimension that we did in the bracket, the third dimension. Now that we do that, so one dimension is 0. Basically, this is why one of the principal stresses that we have must be 0, because we're doing this in 2D. Since we have our lowest one in negative, this sigma 2, which is supposed to be in the middle, should be 0, because it's between our negative stress value and the positive value. Therefore, our sigma 2 is going to be 0 ksi, not the value that we just calculated. Now, that value that we just calculated, negative 6.985, is going to be our sigma 3, the lowest stress among all. So you have sigma 1 is 31.87 ksi, sigma 2 is 0 ksi, and sigma 3 is negative 6.985 ksi. How can you find our shear stress maximum? The rule of thumb is you have to look at the circles. We have 2, 3, 1, 2, and 1, 3. What is the largest circle here? The 1, 3 circle. The biggest circle that we have is going to give us the maximum shear stress. So we're going to get the sigma 1 minus sigma 3 divided by 2. So 31.87 minus 6.985. So it's going to be 31.87 plus 6.985 divided by 2. It gives you 19.43 ksi. Ironically, we actually just got the radius. So we can say, based on the calculation that we have, the maximum shear stress is equal to the radius of the circle that we have.